Okay, let me say something about exercise 12-4. 12-4 talks about the map cis. Cis maps R to the unit circle in the complex plane. So here I drew the number line R. So just say, right? This is basically just the number line R, and then this is T in the complex plane. Now what cis does is it wraps R around T. The zero, right? The zero goes here to this point because cis of 0 equals 1. Now as you move along the real axis in this direction, then if you take cis of any real number, so for instance, this here, that's cis of pi over 2. Right? And then this is cis of pi. Now, because there's no R, that means that R is 1, so you're always staying on the unit circle. This is cis of 3 pi over 2, because the angle or argument is 3 pi over 2. Then we go all the way around, and this is back to cis of 2 pi. Okay, so cis of 0 is equal to cis of 2 pi is equal to cis of 4 pi, and so on. So that's what's said here. Cis of everything in this set is equal to 1. Right? So cis is definitely not a 1-to-1 onto map. It's definitely not a bijection. Well, we can write cis inverse of 1 as this set. Right? So let's follow along with some of the other examples and prove that this set is a subgroup. Now, how do you prove a set is a subgroup? It's a subgroup of R. Now, this R is an additive group. So you need to, give a citation down here. Now here, a subset H of a group G is a subgroup if and only if these three conditions are satisfied. Now we're using H as this set minus 4 pi, minus 2 pi, 0, 2 pi, 4 pi, ... You can also write this as 2 pi times z, because it's every integer multiplied by 2 pi. So this H here refers to this set. This G refers to all real numbers, because we're looking at the subset here as a subset of real numbers. Okay? So you have to prove these three things. The identity is G is an H, the subset is closed under the operation, and the subset is closed under inverse. Now we have to translate this, because now we're dealing with the additive group. So if we translate this, the identity, what is the identity in R? Well, since it's an additive group, the identity 0, now instead of G, we have to say R, is in 2 pi z. So that's what you have to prove here. That's okay. All right, now next one. Again, because we have an additive group, this is a little bit different. Here, let me make this bigger so we can see what the let's look like. Okay, so instead of H1, H2 is in H, we have to say, in this case, we have to say, instead of H1 plus H2, we would have to say if, let's call this, well, since this is 2 pi n, so we can say if 2 pi n1 and 2 pi n2 are elements of 2 pi z, then here it says H1, H2 is in H, but now the group operation is addition. So you'd have to say 2 pi n1 plus 2 pi n2 is an element of 2 pi z. That's what you have to prove here. That's closed under the operation. Okay, now this one here, again, to translate into this current case, we're thinking of H, we're replacing the H with 2 pi z. So I say if, and I can say 2 pi n is in 2 pi z. Then, now, because it's an additive group, the inverse here should be the additive inverse. So that would be minus 2 pi n. is in 2 pi z. All right? So when you have additive groups, you have to translate the times into a plus because the plus is the group operation. And you also have to translate inverse into minus because the negative is the negative is the additive inverse. Right? So that's how you will prove that this this set 2 pi z, this should be 2 pi z here. And this should be 2 pi z. Okay. Right. Now, so we've gotten the group, we've gotten the subgroup, which is 2 pi z. Now, what are the cosets? Now, we can go back to, I think I have it still here, this picture here, when I did 12, 1, 10. Look at the cosets. How do you get the coset of a group? First, you take the group, and then you take an element that's not in the group, and you take that element, first you take the subgroup, then you take an element that's not in that subgroup, but it's in the big group, and you add that to every element in the subgroup. And you keep doing that until you exhaust all the elements of the big group. So what do we have here? In our case, we have, let's switch back to blue. Okay. So what we want are the cosets of 2 pi z, okay, in R. Okay. So to get those, let's draw our picture again, and I'll draw the schematic picture again. Here I'll draw, this is my schematic picture of R, and then 2 pi z is in here somewhere. Now you have to take something that's not in 2 pi z. Let me call it x. It's a real number. Now I take x plus 2 pi z. That's going to be a coset in R that contains x. Then take another one, x prime plus 2 pi z. And you just keep making cosets until you fill up R. Now what does one of these cosets actually look like? Let me draw R as a number line. Okay, and I'll draw 2 pi z, 0, 2 pi, 4 pi, minus 2 pi, minus 4 pi. Okay, and let's pick a number that's not in 2 pi z. So let me just pick x here. And what I do is I take x plus every element in 2 pi z. So x is x plus 0, and x plus 2 pi is going to be here. X plus 4 pi is going to be here. And then x plus minus 2 pi is going to be here. And x minus 4 pi is going to be here. Okay. So you can see the elements of this coset are also periodically spaced. Sorry, I didn't draw these last two very well. Let me place it a little bit better. Well, actually, I think I did do those well. I just didn't do my first one very well. Let me get rid of this one. I think I forgot that I put my, okay, so here, let's do this. My x is more down here. Okay, and then you can see x is in the same position relative to the multiples of pi. Now, suppose I take a different x, which I could do. Let's call this x prime. Let's put x prime kind of in the middle. Okay. Now, if x prime there, then what are the elements of this coset? Well, I take x prime plus every multiple of 2 pi. So here we'd have x prime plus 2 pi. Here I'd have x prime plus 4 pi. Here I'd have x prime minus 2 pi. And x prime minus 4 pi. And so on. Okay. So any real number x that I choose gives me a coset. Now, some of these cosets will overlap. For instance, the coset that I would obtain from x is the same coset that I would obtain from x plus 2 pi. But that's okay. We can have duplicate cosets. That's okay. All right, so let's see what the next part tells us. Next part tells us we want to show that this group, 2 pi z, is a normal subgroup of R. And I would just say go back to the section on normal subgroups and see why that's so. You can find a convenient theorem that tells you that this is a normal subgroup. Hint is to use a property of R. R is a special kind of group that has In fact, all the subgroups of R are normal, and you can figure out why if you go back to the normal subgroup section in the earlier chapter, in the cosets chapter. All right, now, prove that the factor group R mod 2 pi z is isomorphic to T. So let's talk about that. Okay. So that's our next part here. Sorry. Let's see why it's doing that. There, I think I got it adjusted now. So we want to prove that the factor group, oops, all right, sorry, let's get back. It's acting funny. We'll get there. So the next thing to do is to prove that R mod 2 pi z is isomorphic to T. So we'll have to define an isomorphism. Okay. Now we want to use cis. We've been talking about cis, so we'll use cis. All right, now remember what this is. This is the set of cosets. And cosets have the form x plus 2 pi z. Now notice that cis of x plus 2 pi n, what happens when I take x plus 2 pi n and I take the cis of that? Well, cis is the complex argument. 2 pi n just wraps around an integer number of times. That's the same thing as cis of x. Okay. Yeah. So what we can do is we can define cis of the entire coset. Okay, so let me just be a little bit more explicit here. This means that cis of x is equal to cis of x plus 2 pi equals cis of x plus 4 pi equals ... equals cis of x minus 2 pi equals cis of s minus 4 pi equals ... So in fact, cis gives the same value for every point in the coset. Every point in the coset will have the same value of cis. So in fact, I can simply define the value of cis on the coset. We can define cis of x plus 2 pi z, which is the coset, as equal to cis of 2 pi x, cis of x. Okay, because this value of cis agrees for every point in the coset. Okay, now what you're going to want to show is you want to show, first of all, you want to show that this function, that cis defines an isomorphism. Well, that's not, first of all, that's what you want to show. That's what you want to show, totally. An isomorphism from x plus 2 pi z to T. So you have to show two things. First of all, you have to show that cis from, I shouldn't say x plus 2 pi t. I should say, erase that. I should say it this way. I really should say it, the set of cosets, which is the set x plus 2 pi t, 2 pi z. And you can write that as R mod 2 pi z. Right, the set of cosets of 2 pi z in R could be written as R mod 2 pi z. Okay, so first thing you want to show that cis mapping from R mod 2 pi z to T, to set T, is a bijection. Okay, so that's one-to-one and onto. Okay. All right. Now there's two ways to do this. One is you can show one-to-one and onto directly. Another way you can do it is you can show that this cis has an inverse. So let's say a little bit about both of these. First of all, how would you so cis from here to here is one-to-one? Well, you would have to take you'd have to take elements from two different cosets and show that they have two different results. Okay, so if I have to show one-to-one, let's say suppose we have x and x prime in two different cosets. Which means that x minus x prime, if they're not in the same coset, is not a multiple of 2 pi. Okay, x minus x prime is not a multiple of 2 pi. Right. Then you can use an equation, there's an equation relating cis of x prime, and cis of x minus x prime. Go back to your rules about cis, and you can use an equation relating these three to show that cis of x is unequal to cis of x prime. And this will show that cis acting on the cosets is one-to-one. Why is that? Because if we have elements from two different cosets, they get two different cis results. Okay, so the value of cis on one coset will not be the value of cis on the other coset. Okay. Then on to, I think that you need to show for any z in T, there exists an x in R such that cis of x equals z. All right, so that's how you would show onto.